Okay, so now we're going to talk about something called orbital notation or orbital diagrams. And this is going to show, this is pictures, and it shows how the electrons are actually arranged within the orbitals so that you can kind of almost visualize them. So orbital notation is, first of all, it's based on electron configuration. So you have to master that before you jump into this. It's in a method of illustrating how the electrons are arranged within the orbitals of an atom. First rule, each orbital is represented as a line. So if you have an S orbital, you're going to draw one line. But when you get to the P's, remember there were 3 of those. Okay, look back to our Bohr model. There were 3 P orbitals. We're going to draw 3 lines as a group. The D's, we're going to draw 1, 2, 3, 4, 5. And then the F's, we're going to draw 1, 2, 3, 4, 5, 6, 7 lines. So each orbital is represented as a line. And then after the orbitals, so this is where I was talking about p orbitals drawn as a group of 3 lines. Each electron you're going to draw as an arrow, so either pointing up or pointing down. And a lot of times I do my arrows like that because then they it's easier, it's faster. So you're going to draw an arrow for each electron pointing up or down. So first rule you have to deal with this is something called the Pauli exclusion principle. It says that the maximum of 2 electrons can occupy a single orbital, but only if they have opposite spins. So when you have one line, one goes up, one goes down. That's kind of the rule. Okay? So each electron has an associated spin. This is referring to the fact that the real Pauli exclusion principle says no 2 electrons can have the same 4 quantum numbers. And so one has this spin quantum number and the other one has the opposite direction. So that's what his rule is. Then Hund's rule comes along and says that if you have equal energy orbitals, so P, D's, and F's, they fill up individual orbitals first before they share, and they go in with the same direction. Okay, and I'll give you an example of that. So you put electrons into degenerate orbitals with parallel spins before they share. So, for example, if I had to do fluorine, so fluorine is 1s2. I'm not going to do the electron configuration. I'm just going to draw it. All right. So the good grief. The orbital notation, 1s on the bottom, 2s on the bottom, and then the 2 p's get 3 orbitals, 2p. 1s2, 2s2. Notice they're spinning opposite directions. And when I get to this one, because it's 2p5, I go 1, 2, 3, 4, 5. So I fill them up separately first, and then I make them share. Okay, it's kind of like bedrooms in a house, right? If you have 3 bedrooms in your house and there are 3 kids, each kid gets their own room, A, B, and C. If you have 4 kids, you might have to share a room. But unless you do, they all take separate rooms. So if I was doing manganese, that's got 25 electrons. It's argon, 18, 4s, 1, 2. And then you go into 3ds, 5 lines. You have 5 electrons to go. 1, 2, 3, 4, 5. Don't pair them up. Put them all in separate rooms before they share. Argon is neon, 3s, 1, 2, 1, 2, 3, 3p, 1, 2, 3, 4, 5, 6. Okay, this is why noble gases are so stable and they can be used in our shortcut method, is because everything about them is completely filled and paired up. Okay, I'm going to erase the ink on the slide. Cobalt is argon, 18, 4s, 1, 2, 3d, 5 of them, 7, 1, 2, 3, 4, 5, 6, 7. And it doesn't matter where you put the last 2 as long as they spin the opposite direction and that you have 3 guys that are unpaired. If I was to do lead, xenon, 54, 6s, 1, 2, then the 4f, all 7 orbitals, 4f, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, then the 5ds, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5d10, and then you get to the 6p's, which is only 2. Pick any 2. As long as they go the same direction and they are not paired up. Doesn't matter.